usually when you're racking a standard server in a data center, there's this, I don't know, this comforting predictability to it, right?
Absolutely, yeah.
It's almost like commercial plumbing. You slide the 1U chassis into the rack, you plug in the redundant power supplies,
Yeah.
Snap in the CI6 or the fiber cables, and, well, the link lights blink green.
And you're in business.
Exactly. You're in business. You know exactly what that box is going to do, how much heat it's going to generate, and like how it's going to talk to the rest of the network.
Right, because it's entirely standardized. I mean, we've spent decades, literally decades, perfecting the x86 architecture.
Yeah.
Standardizing the PCIe slot layouts, mapping out, standard aisle cooling requirements. The whole IT procurement industry is built around that predictable plug-and-play model.
But then tomorrow, a forklift drops an 8-figure AI GPU cluster on your loading dock.
Yeah, and that's where the panic sets in.
Right. Because if you evaluate or purchase or even try to rack that machine the way you evaluate a standard web server, you're not just going to bottleneck your network. I mean, you will waste millions of dollars, full stop.
Oh, without a doubt. The plug-and-play standard is just dead here.
Dead.
Yeah.
So we are looking at a procurement landscape that is, well, it's murky, it's filled with undocumented bottlenecks, and frankly, it's full of vendor traps.
It is, because people who have spent a decade, mastering traditional network fabrics in enterprise IT,
Right.
they're suddenly being asked to sign off on these massive infrastructure bids filled with acronyms that simply did not exist in this context 5 years ago.
Yeah, it's a completely different language.
You're dealing with hardware that operates on fundamentally different physical and, frankly, mathematical principles.
And that is exactly what we're tearing apart today on this deep dive, because we got our hands on a highly detailed technical briefing document.
A really fascinating one, too.
Yeah, it was written specifically for government IT procurement officers navigating the landscape in 2026. So this is tailor-made for those of you listening who have networking systems or like electrical engineering backgrounds.
Right. You understand TCP/IP, you understand standard compute.
But now you're tasked with navigating this incredibly complex world of modern GPU servers. So our mission today is to translate the overwhelming hype and, honestly, the impenetrable spec sheet jargon of AI hardware into a practical, BS-free toolkit.
Which is desperately needed.
Yeah. We're going to arm you with the precise, technical questions you need to ask vendors so you don't get taken for a ride.
Because to even begin evaluating a bid, I mean, we really have to throw out our fundamental assumptions about what a computer is actually supposed to do.
Okay, let's start right there. The paradigm shift. Because we've been making standard CPU central processing units faster and faster for decades, right?
Right. Moore's Law, multi-core processors, all of that.
Exactly. So my first question is always, why can't I just take a top-of-the-line server CPU, give it a massive chunk of RAM, and tell it to run an AI model? Like, why do we need this entirely separate category of silicon taking up space in the rack?
Well, it comes down to a fundamental mismatch between the physical architecture of a CPU and the mathematics of a neural network.
Okay, break that down for me.
Sure. So think about what a traditional CPU is physically engineered to do. A modern server CPU today might have, 64, maybe 128 cores.
Yeah, somewhere around there for the high-end stuff.
Right. And those cores are massive. They are incredibly complex, and they're designed to execute highly intricate branching logic. They are built for unpredictability.
Unpredictability in the code. You mean like if the user clicks this button, load this database, but if they click that button, trigger this error message, that sort of thing.
Yes, exactly. Yeah. Context switching, branch prediction, running an operating system with thousands of background threads all competing for attention. A CPU is brilliant at navigating sequential logic, where the next step depends on the result of the previous step.
So if we put this into like a networking or civil engineering context, a CPU is like a highly complex, heavily threaded, single-lane highway system.
Oh, okay, I like where you're going.
It's got incredibly sophisticated traffic lights, right? It can handle any vehicle, going to any destination, rerouting them dynamically on the fly based on changing traffic conditions.
That is a very solid way to visualize it. It's smart, but it's dealing with things one at a time, sequentially. But now, look at an artificial neural network. AI does not think using complex decision trees.
Right, there's no if-then statements in a neural net.
No, not really. An AI model, whether it's a large language model or an image generator, is mathematically just a series of massive grids of numbers, matrices.
Just billions of weights and parameters.
Exactly. So when data moves through that network, the underlying mathematical operation is almost entirely matrix multiplication. You are taking a huge grid of numbers, multiplying it by another huge grid of numbers over and over and over again.
So there isn't a lot of branching logic at all. It's just a tidal wave of arithmetic.
There is almost no branching logic in the core execution. It's deterministic parallel math. So if you give that task to a 64-core CPU, what happens?
I'm guessing it chokes.
Well, those brilliant, complex cores are going to spend 99% of their time idle, waiting for the one core doing the math to finish its sequential multiplication. The CPU is over-engineered for logic and severely under-engineered for raw parallel throughput.
Which brings us to the GPU, the graphics processing unit. I mean, I know the origin story here is that these were built for video games, right? For pushing pixels on a screen.
Yeah, and the connection between video games and artificial intelligence is honestly just a beautiful mathematical coincidence.
Really? A coincidence?
Pretty much. Think about it. If you're rendering a modern video game at 4K resolution, you have over 8 million pixels on the screen at any given moment.
Right.
To figure out what color each of those pixels should be, you have to calculate lighting, shading, geometry for every single pixel, usually 60 times a second.
Oh, wow. Yeah, that's a lot of math.
But you don't need complex branching logic for that. You just need to do the exact same simple math equation 8 million times simultaneously.
Okay, so going back to my highway analogy from earlier, a GPU isn't a complex interchange with smart traffic lights. A GPU is like a 10,000-lane dirt road where every single vehicle has to drive perfectly straight at the exact same speed, doing the exact same thing at the exact same time.
Yes. And that is physically how a data center GPU is constructed. Instead of 64 complex cores, a modern GPU has tens of thousands of microscopic, highly simplified cores.
Wow, tens of thousands.
Yeah. And around 2012, researchers realized that simulating the synapses of a neural network requires the exact same parallel arithmetic as rendering a 3D polygon.
That's wild.
It is, and that realization is the entire foundation of the modern AI industry.
Okay, so as a procurement officer, the foundational mental model here is that you are not buying a faster computer. You are basically buying an industrial calculator optimized for parallel matrix multiplication.
That's a perfect way to put it.
And because it's a fundamentally different machine, the vendors use a completely different language to sell them to you. Like, if a vendor slides a spec sheet across the table and you start looking for clock speeds or by 86 instruction sets, you're just dead in the water.
Oh, absolutely. The spec sheets for these machines are a total minefield. They are designed to highlight massive, eye-popping numbers that often obscure the actual real-world performance of the hardware.
So we really have to decode the terminology, starting with the silicon itself. Let's dive into the core types. The briefing dives deep into the different types of cores on these chips, specifically highlighting CUDA cores and Tensor cores.
Right.
Now, I know CUDA is an NVIDIA trademark, but the architectural concepts kind of apply across the board to AMD and others, right?
Yes, the functional concept is universal.
So what is the actual mechanical difference between a CUDA core and a Tensor core?
Okay, so a CUDA core is the general-purpose parallel muscle we were just describing. It is a simplified core, yes, but it's still programmable to do a wide variety of parallel tasks.
Like what?
Well, you can use CUDA cores for physics simulations, fluid dynamics, rendering graphics, or just standard parallel math. But as AI models grew exponentially in size over the years, even thousands of CUDA cores weren't fast enough to handle the sheer volume of matrix multiplication required.
So the hardware vendors physically altered the silicon to hardwire that specific math into the chip.
They did, and that is exactly what a tensor core is. It's a specialized circuit physically etched into the silicon that is designed to do one thing and one thing only.
Which is?
A matrix, multiply, and accumulate operation.
Okay, that sounds intense.
It's actually very specific. It takes two small matrices, multiplies them, and adds the result to a third matrix in a single hardware clock cycle.
Just boom, done.
Boom, done.
So mapping this back to networking hardware again, because I love these analogies.
Let's hear it.
CUDA cores are like a general-purpose router running software to do routing table lookups, right? It handles parallel streams of packets. It can handle any protocol. But there's a ceiling on the throughput because it's still doing generalized processing.
Right. There's always a software overhead.
But a tensor core is an ASIC, an application-specific integrated circuit. It is a custom hardware fast path built specifically to forward one exact type of traffic at wire speed. It's inflexible, but for that one job, its throughput is astronomically higher.
That maps perfectly. It's an ASIC for matrix math. And this is crucial because when a vendor boasts about the performance of their AI chip, They are almost exclusively quoting the theoretical maximum throughput of those tensor cores.
Assuming your software actually uses them.
Exactly. Assuming your software is perfectly optimized to use that specific hardware path. Because if your developers write code that accidentally falls back to the general-purpose CUDA cores, your performance will just drop off a cliff.
Yikes. Okay, so that covers the physical silicon, the cores. But here is where the spec sheets get incredibly deceptive. The briefing talks about performance metrics, and it introduces something that drives traditional IT folks completely crazy.
Oh, I know you're going to bring up the fuzzy math.
Yes. Because in standard computing, if I buy a processor that calculates data, it calculates it perfectly. If I'm calculating a bank transaction or, I don't know, a satellite trajectory, the math has to be precise down to the final decimal.
Right. There is no margin for error.
But AI hardware uses precisions that actually change.
Yeah, this is arguably the most critical technical concept for a procurement officer to grasp when they're reading a bid. It's all about the precision formats, meaning how many bits of memory the system uses to store a single number.
In standard computing, we use 32-bit precision, right? FP32?
Yes, FP32 or 32-bit floating point. It gives you a massive range of values and incredible decimal accuracy. And for years, early AI models were trained using FP32.
Makes sense.
But researchers quickly realized there was a huge bottleneck. Moving 32 bits of data from the memory to the processor takes time, and it consumes precious bandwidth. So they asked a really bold question: do neural networks actually need perfect mathematical precision to guess the right answer?
And I'm assuming the answer is no, because neural networks are inherently probabilistic anyway, right? Like they aren't calculating a rigid formula, they're just finding statistical patterns and noise.
Exactly. An AI model is basically a giant game of hot or cold. If the math is slightly fuzzy, the overall pattern of the data remains intact, and the network still arrives at the correct output. So they decided to just cut the precision in half. They moved from FP32 down to FP16 16-bit precision.
Okay, let me stop you there. Because if you drop half the bits, you are fundamentally changing the numbers. You are rounding them off aggressively.
Yeah.
How does the model not completely break down and just output garbage?
It's a great question. Think of it like a digital photograph. If you have an incredibly high-resolution, uncompressed raw image, you can zoom in and see individual pores on a person's face.
Right. That's our FP32.
Right. Now, if you compress that image to a smaller JPEG, you lose that microscopic detail. The exact pixel values physically change. But if you look at the whole picture on your screen, you still immediately recognize that it's a picture of a face. The macro structure survives the compression.
Oh.
Neural networks operate on the macro structure of the data. They don't care about the microscopic pores, they just care that it's a face.
And the hardware benefit of that compression must be massive, because if a number only takes 16 bits instead of 32 bits, you can fit twice as many numbers in the exact same physical memory chip.
Yes.
And because the data packets are half the size, you can push them through the internal memory bus twice as fast.
It literally doubled the speed of AI training overnight. Just a software shift.
Yeah.
FT16 quickly became the industry standard, but of course they didn't stop there.
Because if 16 works, why not go lower?
Right. If 16 bits works, what about 8 bits? FP8.
Quartering the original precision?
And drastically reducing the memory footprint all over again. Moving a model from a higher precision to a lower precision is a software process called quantization. You are literally rounding off the numbers, grouping them into smaller and smaller buckets.
Does the model get dumber?
There is a slight degradation in the AI's accuracy at FP8, yes. But the speed gains are so enormous that it has become incredibly popular, especially for inference.
And inference is just running the model in production to answer user queries rather than training it from scratch, right?
Exactly. But the briefing for 2026 takes this even further. The newest flagship chips on the market, like NVIDIA's Blackwell and AMD's newest Instinct lines, feature native support for FP4.
4-bit precision.
Yeah. At 4 bits, you are essentially representing a complex parameter with only 16 possible values total.
That sounds absolutely absurd. How does it even work?
It sounds like it shouldn't work. But with advanced quantization algorithms that scale the values dynamically across blocks of data, the models retain an astonishing amount of their intelligence even at FT4.
Okay, I understand the engineering behind it. It's fascinating. But as the person holding the checkbook, how does this get me in trouble in a bid meeting?
Because of the performance metric the vendors use. TOPS or tera operations per second.
Right.
A hardware vendor wants the number on their brochure to be as large as physically possible. So if they measure their chip's performance at FT32, the number might be, let's say, 100 TOPS.
Okay.
But if they measure that exact same physical chip at FP4, because the data is so much smaller and moves through the pipes so much faster, the throughput spikes to 800 TOPS.
Oh, I see the trap. So vendor A submits a bid claiming their server hits 800 TOPS. Vendor B submits a bid for a cheaper server, claiming it hits 200 TOPS. On paper, vendor A looks 4 times faster.
Right.
But vendor A might be quoting FP4 performance, and vendor B is quoting FP16 performance.
Exactly. And here is the kicker. If your in-house developers are running older, legacy models that haven't been quantized and absolutely require FP16 precision to function, vendor A's server isn't actually 4 times faster for your specific workload.
Wait, really?
Really. In fact, it might be exactly the same speed or even slower once the hardware is forced to run at the higher precision. If you do not demand that vendors explicitly define the precision level tied to their performance claims, you are comparing apples to elephants.
That is a phenomenal trap to avoid. Wow. And the briefing mentions one more mathematical sleight of hand in these spec sheets. Sparsity, or the magic zero trick.
Yes. Sparsity.
Explain the mechanics of this, because it sounds like vendors are just inventing performance out of thin air to put on the brochure.
Well, to understand sparsity, we have to look briefly at how an artificial neuron actually fires. In a neural network, there is a mathematical function of something called a ReLU, a rectified linear unit.
Okay.
Its job is very simple. If the math results in a positive number, it passes that number forward to the next layer. If the math results in a negative number, it just turns it into a 0.
Because in a neural network, a negative signal isn't useful. It just means the neuron shouldn't fire at all, like a brain synapse just staying quiet.
Precisely. The result is that as data moves through these massive matrices layer by layer, up to 50% or more of the numbers in the grid naturally become zeros.
Half the grid is just zeros.
Sometimes even more. Now think about the physical hardware doing the math. If the Tensor core pulls a row of numbers from memory and half of them are zeros, it's a complete waste of electricity and time to actually perform the multiplication.
Because anything multiplied by 0 is 0.
Right.
So the hardware engineers got clever.
Very clever. They built logic directly into the silicon that scans the data matrix right before it hits the arithmetic unit. If it sees a 0, it literally skips the calculation cycle entirely and just outputs a 0, moving instantly to the next number. This is called hardware sparsity.
Honestly, that is genuinely brilliant engineering. It saves power, it saves time. But why is it a trap for a procurement officer?
Because of how it's marketed to you.
Yeah.
If the hardware can skip half the math, it effectively finishes the workload twice as fast, right? So vendors take their baseline performance number, which, remember, is already inflated by using FP4 precision, and they simply multiply it by 2. They call this sparse TOPS.
But hold on, that assumes my specific AI workload actually generates 50% zeros in the first place. What if I am running a specialized scientific model, or like an encrypted data analysis model that generates very few zeros? What if my data is dense?
If your data is dense, the hardware cannot skip the math. The performance drops immediately back to the baseline. You will experience exactly half the speed the vendor promised you on the glossy brochure.
Let's summarize the ultimate spec sheet decoder ring rule for you listening right now. When a vendor hands you a performance number in a bid, it is completely meaningless on its own.
Absolute meaningless.
You must force them to state the precision is at FP32, FP16, FP8, or FP4, and you must force them to state whether that number is dense or sparse. Because if they quote 8,000 TOPS, and you find out it's FT4 sparse, you know that the actual dense FP16 performance of that exact same machine might only be a few hundred TOPS.
You have to align the hardware's quoted metrics with the actual precision and sparsity profile of the software your department intends to run. If you don't talk to your developers before reading the bids, you will be flying completely blind.
Okay, that is incredibly clear. So we have thoroughly decoded the processing cores and the math. But here is the stark reality of AI hardware. Having the fastest tensor cores on the planet is entirely useless if you cannot feed them data fast enough.
Oh, without a doubt. And this is where AI stops being a pure compute problem and turns entirely into a networking and plumbing problem.
And this is where traditional IT engineers really have an advantage once they understand the terminology right.
Definitely. Because the internal architecture of a modern AI server is essentially just a miniature ultra-high-speed network topology.
Let's start with the memory physically attached to the GPU, because this is not the standard DDR memory sticks you just click into a server motherboard.
Not at all. Standard DDR RAM is way too far away from the processor, and the physical traces on a standard motherboard just can't carry data fast enough for AI.
So what do they use?
AI GPUs use a technology called HBM high bandwidth memory.
Okay.
Instead of putting the memory on the motherboard, they manufacture the memory chips, stack them vertically like pancakes to save physical space, and then they place that stack on the exact same piece of silicon packaging as the GPU processor itself, mere millimeters away.
Just shrinking the physical distance the electrical signal has to travel.
Exactly. Physics dictates latency. By placing stacked memory directly adjacent to the compute cores and connecting them with an incredibly wide microscopic bus, they achieve data transfer rates that are literally impossible on standard motherboards.
And on the spec sheets, we'll see terms like HBM3, HBM3E, and HBM4.
Right, those are just generations denoting faster speeds and denser memory stacks.
Now, the briefing emphasizes that procurement officers constantly confuse two vital metrics regarding HBM capacity and bandwidth. We really need to define the physical realities of both for the listener. Let's start with capacity, measured in gigabytes.
Capacity is straightforward. It's the total volume of data the stacked chips can physically hold at one time. In 2026, flagship GPUs typically offer somewhere between 144 to 288 gigabytes of HBM capacity per card.
Okay.
And capacity is a hard gatekeeper. If the AI model you want to run requires 150 gigabytes of memory to load its parameters, and your GPU only has 144 gigabytes of capacity, the model will crash. It will not run.
Wait, I can't just use a page file and swap to a hard drive like a normal server.
No, absolutely not. The latency of swapping to an SSD would cause the AI to stall completely. The math moves too fast. The entire model needs to live in the HBM to function effectively.
So capacity dictates whether the model fits in the brain at all. What about bandwidth measured in terabytes per second?
Bandwidth dictates how fast that data can flow from the HBM memory stacks into the Tensor cores to actually be calculated. The NVIDIA B200, for example, boasts around 8 terabytes per second of memory bandwidth on a single chip.
I want to pause on that number for a second because I don't think people realize how fast that is. A standard 10 gigabit enterprise network connection pushes about 1.2 gigabytes per second.
Right.
This single chip is pushing 8,000 gigabytes per second internally.
It is staggering throughput, and yet, and this is the crazy part, it is still the primary bottleneck.
Really? 8 terabytes a second is a bottleneck.
Yes. For many AI workloads, especially inference, where the model is loaded and just waiting to answer questions, the tensor cores calculate the math so incredibly fast that they actually sit idle, just waiting for the HBM to fetch the next batch of numbers.
So returning to our networking roots, capacity is the size of your storage array. Bandwidth is the speed of your fiber link. You can have a massive storage array holding the entire model, but if your fiber link is too slow, the compute cores are going to starve.
This is exactly why you will often see vendors advertising memory bandwidth just as aggressively as they advertise compute TOPS. Because if your department's workload is heavily bottlenecked by memory bandwidth, buying a GPU with twice the compute power but the exact same memory bandwidth will yield absolutely zero performance improvement.
Wow, that's a huge pitfall. Okay, so what happens when a model is so massive, say one of those trillion parameter foundational models, that it simply cannot physically fit into the 288 gigabytes of capacity on a single GPU?
Well, then you have to split the model across multiple GPUs. You put a piece of the matrix on GPU 1, a piece on GPU 2, a piece on GPU 3, and so on.
But if the matrices are split, the math is split. That means the GPUs have to talk to each other constantly to share the intermediate results of their equations.
Oh, constantly. Millions of times a second.
Which brings me back to something I'm stuck on. Why can't we just use the standard architecture? A traditional server has a motherboard with a PCIe bus. PCIe Gen 5 is incredibly fast. Why can't GPU 1 just send its math results to GPU 2 over the standard PCIe lanes on the motherboard?
Okay, let's actually trace the physical path of a packet trying to cross a PCIe bus in a multi-GPU setup.
Let's do it.
GPU 1 finishes a calculation. It has to push that data down its PCIe lanes, across the motherboard, and into the CPU's memory controller.
Okay.
The CPU then has to interrupt what it's doing, read the data, figure out where it's going, push it back out through a completely different set of PCIe lanes, and finally into GPU 2.
That sounds like a massive routing loop.
It is a massive routing loop. You are taking data generated by a device operating at 8 terabytes per second and forcing it through a CPU memory controller that might top out at a few hundred gigabytes per second, adding massive context switching latency at every single step.
So for AI matrix math, standard PCIe is just a catastrophic bottleneck.
Completely catastrophic. The GPUs will spend 90% of their time waiting for the CPU to pass the messages.
So the necessity of bypassing the CPU completely is what birthed these proprietary interconnects. And the big one everyone always talks about is NVIDIA's NVLink.
Right. NVLink is a dedicated ultra-high-speed network built directly between the GPUs themselves. It completely ignores the motherboard's PCIe bus, and it completely ignores the CPU.
It's just GPU to GPU.
Yes. It is a direct point-to-point mesh. GPU 1 has a dedicated physical lane wired directly to GPU 2, GPU 3, GPU 4, and so on.
And when you need to connect more than just a few GPUs within a single server chassis, you need a switch, right? Just like standard networking.
Exactly. And NVIDIA uses something called NVSwitch. It is a specialized switching silicon designed exclusively to route memory traffic between GPUs over NVLink copper cables.
Right.
Using NVSwitch, you can connect 72 or even hundreds of GPUs in a single rack or cluster, and they can all read and write to each other's HBM memory directly as if they were one giant virtual GPU.
The briefing calls this a scale-up domain, right? Tightly coupling physical hardware in a rack to act as a single logical entity.
Yes, scale-up is the industry term for that.
And AMD has their own version of this, right? Infinity Fabric. And the briefing also mentions an open standard that's trying to break NVIDIA's dominance called UALink.
Yes, UALink is backed by a huge coalition, AMD, Intel, Broadcom, and others. They are aiming to standardize this GPU to GPU memory fabric so you aren't locked into a proprietary NVIDIA ecosystem.
But the physical principle remains exactly the same. Bypass the CPU, bypass standard PCIe, and connect the GPU memory pools directly.
Precisely. But eventually, you hit the physical limits of a single copper mesh. You can't run copper NVLink cables across a massive football field-sized data center. You have to connect multiple scale-up racks together to build a supercluster.
And that transition is called scale-out, connecting multiple massive virtual GPUs across a room. This is where your traditional data center networking background applies directly, but with a twist. The historical standard for scale-out AI fabrics has been InfiniBand.
Right.
Because standard Ethernet TCP/IP just has too much overhead for this.
Way too much overhead. If an AI training run requires 1,000 GPUs to perfectly synchronize their weights, any packet loss or latency jitter causes the entire cluster to pause and wait for the retransmission.
Which wastes an unbelievable amount of expensive compute time.
Exactly. InfiniBand is a lossless, incredibly low-latency designed designed specifically for this kind of high-performance computing.
But Ethernet is fighting back, right? The briefing highlights ROCe RDMA over converged Ethernet.
Yes, the networking industry absolutely does not want to lay separate InfiniBand cabling just for AI. They want to use their existing Ethernet infrastructure. Technologies like NVIDIA's Spectrum-X or the broader standards from the Ultra Ethernet Consortium are pushing Ethernet to achieve the lossless, low-latency performance of InfiniBand.
But whether a vendor bids an InfiniBand backend or a ROCe backend, the underlying magic protocol that makes it all function is RDMA, Remote Direct Memory Access.
Yes, RDMA is the key.
Let's break down exactly how RDMA works, because it fundamentally alters how network interfaces interact with memory.
Okay, think about a traditional network packet. A web server wants to send data. The application copies the data into the operating system's buffer.
Right.
The OS adds TCP headers, copies it to the network interface card driver, and the NIC sends it over the wire. On the receiving end, the NIC interrupts the receiving CPU. The CPU copies the data from the NIC buffer into OS memory, strips the headers, and finally copies it into the receiving application's memory.
That is multiple context switches, multiple memory copies, and constant CPU interrupts just to move one tiny piece of data.
RDMA bypasses all of that entirely. With RDMA, the sending GPU tells its network interface card, take this block of memory and put it exactly at this physical memory address on server B.
And then what?
The NIC reads the GPU's memory directly via hardware, fires it across the network, and the receiving NIC writes it directly into the receiving GPU's memory.
So the operating systems are completely unaware the transfer even happened?
Completely unaware.
The CPUs are completely bypassed?
Yeah.
It is pure hardware-to-hardware memory injection?
It reduces latency from milliseconds down to microseconds. If you do not have an RDMA-capable backend fabric, whether that's InfiniBand or specialized Ethernet, you simply cannot effectively scale AI workloads across multiple racks, period. The cluster will choke on its own communications overhead.
Wow. Okay, there's one last architectural shift in the plumbing section. We've talked a lot about bypassing the CPU, but what if we just merge them? The briefing highlights unified or coherent memory architectures, specifically pointing to NVIDIA's Grace Blackwell superchip and AMD's MI300A.
This is a fascinating development. Historically, the CPU has its massive pool of slow BDR RAM, and the GPU has its tiny pool of blazing fast HBM. They're separated by the PCI bus. If the CPU needs to feed data to the GPU, it has to copy it across that bus. It's a toll booth.
A very slow toll booth.
Right. What a unified architecture does is physically link an ARM-based CPU and the AI GPU on the exact same board with a massive interconnect, allowing them to share a single coherent memory space.
Meaning the CPU and the GPU are literally looking at the exact same physical memory addresses simultaneously.
Exactly. Zero copying. If the CPU pre-processes a massive database query, the GPU can instantly execute an AI search on that exact same data without waiting for it to be moved over a bus.
That's incredible.
For workloads involving massive databases or complex multimodal data streams, a unified architecture completely eliminates the traditional system bottleneck.
So if a vendor bids a Grace Blackwell system, they aren't just selling you a faster GPU, they're selling you a completely redesigned server architecture.
Exactly.
Okay, we have decoded the internal plumbing, the precision formats, and the raw math capabilities. But how do we actually calculate how many of these ultra-expensive machines your department needs to buy? Like if a department head says, we want to run a custom AI chatbot, how do you size the hardware?
That takes us to the sizing equation.
And the fundamental dichotomy of AI, training versus inference.
Sizing AI hardware is not like sizing a web server where you just guess the number of concurrent users. You can mathematically calculate your memory requirements with startling accuracy, provided you know the size of the model.
Let's do the math live on the microphone for the listener. Let's say a government agency wants to deploy a secure internal documentation system. The developers want to use an open source model with 70 billion parameters, a 70B model.
Okay, very common scenario.
How much physical memory is required just to turn the machine on and load the model?
It maps directly back to the precision formats we decoded earlier. The rule of thumb is simple math. If your developers insist on running that 70 billion parameter model at FP16 precision, every single parameter requires roughly 2 bytes of memory to store.
Okay, let's calculate that. 70 billion parameters multiplied by 2 bytes each. That is 140 billion bytes, or roughly 140 gigabytes of memory, just to store the static weights on the GPU.
Correct. Now look at your spec sheet. A standard older generation GPU might only have 80 gigabytes of HBM.
So the 140 gigabyte model physically will not fit on one card. You would have to buy a multi-GPU server and link them with NVLink just to pool enough memory to load the model.
Exactly. But what if your developers use quantization? What if they compress that 70B model down to FP8 precision?
Well, at FP8, each parameter only takes 1 byte. So the memory requirement instantly drops from 140 gigabytes down to 70 gigabytes.
And suddenly, that massive model fits comfortably onto a single, much cheaper 80 gigabyte GPU.
Right.
You just saved hundreds of thousands of dollars in hardware by changing a software flag.
That is massive leverage for a procurement officer.
And if they can leverage the 2026 hardware natively supporting FP4, it drops to roughly half a byte per parameter.
Which means our massive 70B model now only requires 35 gigabytes of memory. The hardware footprint just collapses entirely.
It does, but wait, loading the model weights is only half the sizing equation? That just puts the brain on the table. You need memory for the brain to actually think and process a user's query. This is called the KV cache, or key value cache.
What physically is the KV cache? Like, what is it actually doing?
When you have a conversation with a chatbot, it needs to remember what you said 3 sentences ago to maintain context, right?
Right.
The KV cache is a dynamic chunk of memory allocated on the GPU to store the mathematical representations of the ongoing conversation history.
So the longer the document you ask it to summarize, or the more users concurrently querying the model, the larger the KV cache grows in memory.
Exactly. If you only provision 70 gigabytes of memory for a 70 gigabyte model, the moment a user types a prompt, the system will crash out of memory. You always have to provision substantial overhead for the KV cache during inference workloads.
Okay, so that math covers inference running the model. What if the department head says, we want to train our own model from scratch, on classified government data. How does the math change for training?
It doesn't just change, it violently explodes. The memory required to run inference is tiny compared to training.
Why is it so much higher?
During a training run, the GPU cannot just store the static weights. It has to calculate how wrong the model is, calculate the adjustments needed for every single parameter, and store all of that intermediate math.
The briefing mentions storing gradients and optimizer states.
Yes. The math used to adjust the weights is incredibly complex and requires massive memory overhead. A very rough rule of thumb is that full training requires at least 4 times the memory footprint of just storing the model.
4 times. So if our FP16 model required 140 gigabytes to run inference, it would require over half a terabyte of working HBM memory just to train.
Easily. And that is before you even account for loading the massive batches of training data itself. You immediately blow past the capacity of any single GPU on the market. You are now forced to procure a massive NVLink connected multi-GPU cluster just to handle the memory footprint of a single training run.
Which brings us to arguably the most valuable question an IT procurement officer can ask in any AI strategy meeting. Are we training or are we just doing inference?
It seems basic, but the failure to distinguish between the two is the leading cause of wasted budget in AI procurement today.
I can completely see how it happens, though. An IT director reads an article about how OpenAI built a massive 100,000 GPU cluster to train their new model. So they assume they need a multi-million-dollar NVLink cluster for their own department.
But most government departments are not pre-training foundational intelligence from scratch. That is the domain of giant AI labs.
Right.
Government departments are typically taking an existing pre-trained model and fine-tuning it, or just running straight inference to process tax forms, summarize policy documents, or run an internal help desk.
And as we established, inference workloads care heavily about memory bandwidth and capacity, not necessarily massive interconnected compute. You can run inference exceptionally well on fewer, cheaper, or even previous generation GPUs connected via standard networking.
Exactly. If an internal requirements document blindly demands a fully meshed, liquid-cooled NVLink training cluster for what turns out to be a relatively straightforward document processing inference job, you need to push back aggressively. Asking that single question can literally save tens of millions of dollars on a single contract.
Okay, so armed with that sizing math, you are finally ready to look at the market. Let's analyze the 2026 vendor landscape. We have to start with the undisputed heavyweight champion, NVIDIA.
Yeah, NVIDIA currently commands 80% or more of the data center AI accelerator market. You really must know their architectural naming conventions to track the hardware generations.
Give us the breakdown.
An older legacy generation was Ampere, like the A100 chip. That was superseded by Hopper, the H100 and H200 chips, which drove the early generative AI boom.
But in 2026, the flagship generation is Blackwell, the B100, the B200, and the Grace Blackwell superchips.
The B200 is a monster of engineering. We mentioned it has roughly 192 gigabytes of HBM3 memory, pushing 8 terabytes per second of bandwidth, and it introduced that native hardware support for FP4 precision we talked about, allowing it to mathematically crush inference workloads compared to the older Hopper chips.
Now, when looking at NVIDIA bids, procurement officers will constantly see 2 acronyms, DGX and HGX. What is the actual functional difference?
It's basically about who builds the box. DGX systems are NVIDIA's proprietary, fully integrated appliances. NVIDIA designs the GPUs, the motherboard, the chassis, the network cards, and they sell it as a complete premium package.
HGX is a reference design then.
Right. NVIDIA sells the core HGX baseboard, which is the GPUs, and the NV switch interconnects to third-party original equipment manufacturers like Dell, HPE, Lenovo, or Supermicro. Those OEMs then build their own customized server chassis, power delivery, and cooling systems around the NVIDIA baseboard.
So if 3 different vendors bid an HGX B200 server, the computational core is identical NVIDIA silicon, but the reliability, the cooling efficiency, the management software, and the support SLAs will vary wildly depending on the OEM who actually built the wrapper.
Exactly. You are evaluating the OEM's integration skills just as much as you're evaluating the silicon.
But let's get to the real reason NVIDIA has an absolute stranglehold on this market. It's not just the silicon. The silicon is fantastic, obviously, but competitors build fast silicon too. The briefing emphasizes something called the CD moat.
CUDA is NVIDIA's proprietary software computing platform and application programming interface. It is the connective tissue that allows developers to write code that actually executes on those thousands of parallel GPU cores.
Why is it a moat?
Because NVIDIA didn't just release a driver and walk away, they spent 15 years funding and building deeply entrenched, highly optimized software libraries for every conceivable AI operation. When researchers built the major AI frameworks like PyTorch or TensorFlow, they optimized them deeply for CUA.
So an entire generation of data scientists and AI engineers learned to write code, assuming a CUDA backend.
Millions of lines of custom AI code are hard-coded to rely on specific NVIDIA software libraries. It is a textbook vendor lock-in.
And developers despise rewriting code.
They absolutely refuse to. If you force a developer onto a non-NVIDIA system, they often have to deal with unoptimized libraries, mysterious crashes, or spend months rewriting custom kernels just to get their model to run efficiently. The Lebenshost of migrating off CUDA often completely eclipses the hardware savings of buying a cheaper competitor's chip.
Which perfectly frames the distant but highly credible number 2 in the market, AMD.
AMD's data center AI line is the Instinct series. The previous generation was the MI300X, and in 2026, the current generation pushing into the market is the MI350X series, with the MI400 architecture on the horizon.
I'm going to push back hard on the NVIDIA dominance narrative here based on the specs in the briefing.
Go for it.
The AMD MI350 series boasts up to 288 gigabytes of HBM memory per card. NVIDIA's flagship B200 has 192 gigabytes. We just spent 20 minutes establishing that memory capacity is the absolute primary bottleneck for running massive inference models.
Right, we did.
So if AMD has significantly more memory, why doesn't AMD just instantly win every single inference bid?
Technically, on paper, for pure inference workloads where memory capacity dictates how many models you can load, AMD offers an incredibly compelling hardware value proposition. You can fit larger models on fewer AMD cards.
So why aren't they 50% of the market?
It comes right back to the software boat. AMD's answer to CUD is an open source platform called ROCm. ROCm has improved massively. It supports major frameworks like PyTorch seamlessly for standard operations. But when you get out to the bleeding edge of AI custom mathematical kernels, complex multi-node scaling across thousands of chips, ROCm is generally considered to be trailing CUD in maturity and stability.
The human element again. It doesn't matter if the AMD hardware is theoretically faster or holds more memory if your department-specific software stack crashes when you try to run it.
Exactly. However, as a procurement officer, AMD is your absolute best friend. They are your primary leverage to prevent NVIDIA from dictating pricing. The briefing strongly advises that you architect your tenders to allow AMD-based bids as competitive alternatives, provided your technical evaluation carefully accounts for any software migration or validation efforts your developers will need to undertake.
That makes a lot of sense. Let's touch briefly on the other players mentioned in the briefing, Intel and Huawei.
Intel has historically struggled to capture significant AI accelerator market share. They are transitioning from their Gaudi line to a new architecture codenamed Jaguar Shores. The briefing advises treating Intel AI bids with standard procurement scrutiny, particularly regarding long-term software ecosystem support.
And Huawei is a unique case dictated almost entirely by geopolitics, the Ascend series, specifically the 910B and the newer 910C.
Right. Huawei was forced to rapidly develop domestic AI chips because strict U.S. export controls cut off Chinese access to top-tier NVIDIA and AMD silicon. Necessity breeds invention.
The briefing notes the 910C is essentially two older 910B dies stitched together to increase performance.
It delivers performance roughly comparable to NVIDIA's older H100 generation. It is highly capable hardware, but it runs on Huawei's proprietary Canon software stack, which has a much smaller global ecosystem than CUDA or ROCm. If you are in a market where Huawei is legally permitted to bid, they will usually compete aggressively on price. But the critical advice here is independent verification. Do not blindly trust the vendor datasheet, because third-party independent benchmarking of the Ascend chips is much scarcer than for US-based hardware.
I want to pivot to a fascinating hardware quirk the briefing brings up. Apple. I see developers all the time running highly capable local AI models on MacBooks or Mac Studios. Why are they able to do that without a dedicated NVIDIA GPU?
It circles back to the unified memory concept we touched on earlier. Apple's M-series chips, the M3, M4 Max, and Ultra variants, are brilliantly engineered to share a single pool of massive high-bandwidth memory between the standard CPU cores and the integrated graphics cores.
You can configure a Mac Studio with nearly 200 gigabytes of unified memory.
Which means a developer can load a massive AI model into that memory pool on a single desktop machine without needing a $40,000 data center GPU. It is a phenomenal tool for local prototyping and running low concurrency inference at a fraction of the power draw.
But the briefing slaps a massive warning label on this for procurement officers.
Yes. Do not attempt to rack mount Mac Studios for enterprise data center deployment. They lack enterprise out-of-band management like IPMI. They lack redundant hot swap power supplies. They lack high-speed RDMA network interfaces. And they do not have a robust ecosystem for multi-node cluster orchestration.
There are workstations.
They are workstations. Keep them on the developer's desk.
So the U.S. Department of Commerce has implemented aggressively shifting export control rules restricting which countries can buy which tiers of AI chips.
The rules classify countries into tiers. Some countries require complex, multi-month licensing reviews just to import flagship chips. Others face an outright embargo. Furthermore, vendors now tightly control the supply chain to prevent smuggling.
The briefing uses an example of a government procurement in Pakistan. What is the practical reality of these laws for the buyer?
You must verify your country's current export eligibility directly with the manufacturer before you even finalize your technical specifications. The laws change rapidly. What was perfectly legal to buy 6 months ago might suddenly require a massive stack of end-user certificates, legal documents, proving exactly who will use the machine and for what purpose.
Do not wait until you award the contract to ask the winning vendor for their export documentation. Make it a mandatory requirement of the initial bid submission.
If you don't, your multi-million-dollar cluster could sit impounded in a customs warehouse for 9 months while bureaucrats argue over licensing.
Which introduces a highly controversial procurement strategy. Sometimes, the smartest move isn't buying the newest hardware.
Exactly. Even if you are legally cleared to buy a flagship B200 cluster, the global backlog might dictate a 12-month lead time for delivery. A fully export-cleared previous-generation GPU, like an H100 or an AMD MI300 that is sitting in a warehouse and can be delivered in 30 days, is often a radically smarter choice for a government project than paralyzing your department waiting a year for the newest shiny object.
But long wait times breed black markets. The gray market warning in this briefing is stark.
If an unknown reseller suddenly emails you claiming they have brand new top-tier flagship GPUs available for immediate delivery at a suspicious discount, while major OEMs are quoting 9-month delays.
Run.
They are smuggled, diverted, or counterfeit.
They are gray market. If you buy them, you get no manufacturer warranty, you get no software support, and you potentially implicate your government department in a violation of international export control laws. You must demand verifiable serial numbers and trace them back to authorized regional distributors. Okay, let's move from legal traps to technical traps. The spec-gaming checklist. We already exposed the precision trick, quoting sparse FP4 numbers when you need dense FT16. We exposed the memory trick, highlighting massive capacity while hiding crippled bandwidth. Let's expose the interconnect trick.
This is a classic vendor sleight of hand. You release a tender asking for an 8-GPU AI server. Vendor A bids a system for $300,000. Vendor B bids a system for $150,000.
Half the price. The procurement officer's eyes light up.
You look at the spec sheet. It has 8 of the exact GPUs you asked for. It has the right CPU. It has the right RAM. So you award the contract to the cheap bid.
And when the developers try to train a model, the system grinds to a halt. Why?
Because vendor B did not use an NVLink baseboard. They took a standard by 86 motherboard and crammed 8 GPUs into standard PCIe slots.
We talked about this, the PCIe bottleneck.
Exactly. They technically met the requirement of 8 GPUs in a box, but they physically crippled the GPU's ability to talk to each other. For multi-GPU workloads, that cheap server is fundamentally broken. You cannot just specify 8 GPUs. You must explicitly specify the interconnect topology. You must demand fully meshed NVLink or InfiniBand, providing X terabytes per second of GPU to GPU bandwidth.
You have to dictate the internal plumbing in the tender, or they will sell you a clogged pipe. And speaking of physical disasters, let's talk about thermal physics, the power and cooling trap.
This is where standard IT procurement officers make career-ending mistakes. A traditional 1U web server draws maybe 500 watts. A traditional data center rack filled with these servers might draw 5 to 7 kilowatts of power total. The room's air conditioning is designed to extract 7 kilowatts of heat per rack.
What happens when I slide a single flagship 8-GPU AI server into that rack?
A single B200 GPU can draw up to 1,200 watts. 8 of them, plus the dual CPUs, plus the massive memory banks, plus the high-speed networking gear. That single chassis can draw 10 to 12 kilowatts.
One chassis draws double the power of a fully loaded traditional rack.
If you try to power on a full rack of these AI servers in a traditional data center hall, you will literally melt the power distribution units, and the standard air conditioning will completely fail to remove the heat. The servers will firmly throttle their performance to a crawl and then shut down to prevent a fire.
Vendors love to leave power and cooling as customer responsibility in the fine print.
You must demand that bidders state the thermal design power, the TDP per GPU, the maximum system power draw under heavy AI load, and the exact physical cooling requirements. The industry is rapidly shifting away from air cooling entirely for these flagship chips. You are looking at direct-to-chip liquid cooling manifolds, requiring specialized plumbing loops connected directly into the server chassis.
You cannot figure this out on the loading dock. You must loop your facilities and electrical engineering teams into the procurement process on day one. Have them sign off on the data center's thermal capacity before you release the tender.
And this dramatically alters your total cost of ownership calculation. Over a 3-year lifespan, the electricity required to power and cool a 10-kilowatt AI server will represent a massive fraction of the total hardware cost. You have to model the TCO accurately.
Let's assume you've navigated the minefield. The contract is awarded, the hardware arrives, and it's time for technical acceptance testing. The briefing is adamant that you cannot just plug an AI server in, see the green lights, and sign the check.
Standard hardware verification is completely insufficient here. First, you use low-level command line interfaces, NVIDIA's MI or AMD's ROCm MI. These tools query the hardware directly, verify the exact GPU silicon model, verify the exact HBM capacity, and verify the firmware versions match your awarded contract perfectly.
But seeing the hardware on a screen doesn't prove it actually performs.
Exactly. Do not rely on the vendor's proprietary cherry-picked benchmarking scripts to prove performance. You must run vendor-agnostic, standardized industry benchmarks. The gold standard is MLPerf. Run MLPerf suites tailored to your specific use case, whether that's image classification or large language model inference.
You are testing to see if the real-world throughput actually hits the numbers they promised, using the precision format your developers actually intend to use.
And you must verify the plumbing. Use the networking command line tools to verify that the NVLink topology is physically active and passing traffic without errors. Verify the InfiniBand or ROCe RDMA connections are established between the nodes.
And finally, the burn-in test.
Yes. You must run the system under sustained 100% maximum AI load for 24 to 48 hours. Monitor the power draw. Monitor the internal temperatures. You're forcing the system to prove that its cooling apparatus can hold the temperatures within safe operating ranges without dynamically slowing down the clock speed's thermal throttling to survive.
Apply all the rigorous verification you would use for a core network switch upgrade, just adapted to the intense physics of AI hardware. We have covered a massive expanse of highly technical ground today. Our mission was to provide you with a conceptual toolkit to confidently lead a pre-bid meeting and protect your budget. You now have the vocabulary. You understand that a CPU handles complex logic, but a GPU handles massive parallel arithmetic. You know the physical difference between general CUDA cores and specialized Tensor ASICs.
You understand the deceptive math of precision formats? You know why an FP4 specification looks vastly faster than an FP32 specification, and you know how vendors use hardware sparsity to artificially double their headline numbers. You know to demand dense precision-specific metrics.
You understand the internal plumbing? You know the critical distinction between memory capacity holding the model and memory bandwidth feeding the cores. You understand the physics of why PCIe fails and why NVLink and RDMA fabrics are mandatory to bypass the CPU and prevent network bottlenecks.
And most critically, you understand the extreme sizing differences between inference workloads and training workloads.
By demanding precise answers to these technical realities, you don't need a PhD in machine learning to be a highly effective procurement officer.
Yeah.
You can identify spec-gaming, avoid vendor traps, and ensure your department actually gets the computational power they are paying for.
Before we wrap up, I want to pose a provocative thought experiment that builds on the architectural realities we've discussed today. We spent a lot of time analyzing NVIDIA's absolute dominance, anchored by their incredible silicon, their proprietary NVLink interconnects, and their massive CUDA software moat.
It feels like an impenetrable fortress of vendor lock-in.
It does today. But consider the massive push right now from the rest of the industry, AMD, Intel, Broadcom, Cisco, to establish open, standardized networking fabrics. Look at ULink, designed to replace NVLink. Look at the Ultra Ethernet Consortium, designed to optimize standard Ethernet to replace InfiniBand.
They are trying to turn the proprietary plumbing into a universal standard.
Exactly. What happens to the market in 5 years if standard open networking protocols become perfectly efficient at routing memory traffic between any GPU from any vendor? If an AMD GPU can seamlessly share a memory pool with an Intel accelerator over standard Ethernet without context switching latency, does the hardware itself eventually become a perfectly commoditized utility?
That's a massive paradigm shift.
If the underlying hardware is commoditized by open networking, does the value of the proprietary CUDA software ecosystem eventually collapse under the weight of open source translation layers? Does the ultimate power in this market eventually shift away from the silicon vendors and back into the hands of the buyers who control the open network fabric?
That is absolutely something to chew on before you sign a 5-year lock-in contract with any single vendor. The plug-and-play predictability of traditional IT might be dead today, but perhaps open networking standards are the key to bringing it back to the AI data center of the future. We've sailed right into the wildest frontier in enterprise infrastructure. But armed with this deep dive, you finally have an accurate map of the minefield. Keep demanding those dense precision metrics, verify your interconnect topologies, and we will see you on the next deep dive.